Well, coming to the last lesson in this chapter, we are going to talk about isolation fault detection. So let's see further. Now, in battery diagnostics and troubleshooting for EV connected vehicles, battery swapping scenarios include unique diagnostic challenge and operational updates that differ significantly from conventional fixed battery EVs. Okay, so in the areas, in the vehicles where battery swapping is common, it has its own unique challenges. Okay, now let's see what is meant by first battery swapping. Battery swapping involves removing a depleted battery pack from a EV and replacing it with a fully charged one at a swap station. It is commonly used in fleet and shared mobility, example electric two-wheelers, taxis, deliverable vehicles, and also battery as storage business models. Now, coming to countries, regions with fast charging infrastructure, the key diagnostics and troubleshooting challenges in battery swapping. All right. So, what are the key troubleshooting challenges when it comes to battery swapping? We will see below. The first is authentication and battery identity validation. So, before swapping, the vehicle and battery ECUs must verify compatibility. Battery must report serial number, firmware version, and health status. So these are all extremely important to have a proper standardization. Now verifying the VIN vehicle identification number, battery binding check in some OEMs, and each vehicle may be authorized to use specific packs. So naturally, when it comes to troubleshooting, if the battery fails identity or authentication, fault code, such some fault code or some DTC code will be popped up. Now, and this fault code will mean that battery pack authentication has failed. Now, talking of, now in this right side figure, you can see a battery swap station. This is what I was talking about. Now, talking about state synchronization between battery and vehicle. Swapping introduces the need to reset and reinitialize state of charge, state of health. Okay, so when it comes to state of charge and state of health, and also the odometer versus usage counter. Now talking to transfer or fetch historic usage profile from battery or cloud. So on the troubleshooting is, if at all there is a SOC mismatch, user sees incorrect range, and then he runs synchronization protocol and perform initial voltage check during the mounting event. Now, talking about the pre-swap and post-swap diagnostics at the station, this is a very important step as far as the swapping is concerned. Each battery undergoes a pre-swap checks like cell voltages, insulation resistance, internal temperatures, and also communication integrity like CAN and BLE. Now, talking to the mechanical latch status, this is an important precept because all said and done, cell is a mechanical product and it has to fit in. It had to be fit in perfectly in a very taut manner inside the groove. So mechanical latching is extremely important. Post swap diagnostics. Post contactors closing properly, voltage and current handshake with vehicle VCU. All right. And for example, fault codes. What are the various fault codes that can arise in this scenario? P0AA6 insulation fault detected before reinsertion. P1B10 contactor not closing, and P0A80 battery degradation too high. Okay, so if battery degradation is too high, you can bluntly reject the swap. All right. Now talking about the cloud-centric battery diagnostics and life cycle management. Okay, this is a very state-of-art technology, and but it is more and more being used by many OEMs nowadays. Now, swappable batteries are typically managed by battery cloud platforms which track battery's full usage history, SOH, SOC drift over time, fault logs from each usage cycle, swap frequency and energy throughput. Okay, so these are the various parameters or metrics that are tracked by the cloud-centric battery diagnostics. And diagnostics data can include total cycles used, that means number of charge and discharge cycles. Okay, one cycle means one charge and one discharge. And last 10 fault events. Snapshot from onboard battery management system, estimated SOH, cloud calculated from usage logs, and geofence location, swap station, and usage traceability. Talking about the benefit, cloud can flag a specific pack of retirement or maintenance based on DTC trends and degradation analytics. Okay, now these are the various benefits of the cloud-centric battery diagnostics. Now let's talk about the firmware version and configuration conflicts. All right, swapping can introduce the issues if the battery firmware version is outdated and the BMS parameters are incompatible with vehicle's ECU. Now the BMS reports unsupported configuration and diagnostic action means run compatibility check between firmware versions of VCU and BMS. If failed, OTA update or force reject or swap. Okay, now this is the diagnostic action that need to be taken in case of any failed firmware or configuration conflict. Now we are going to talk about the diagnostic updates in battery swapping context. In the context of battery swapping, what are the various diagnostics that are getting updated or customized in swappable battery ecosystems? Now talking, so first thing is BMS DTC database and add DTCs for swap specific errors like unauthorized pack, mounting sensor error. Second category is cloud diagnostic logic. Use machine learning to analyze swap patterns and detect early degradation. Now talking about the VCU diagnostic routines, enhanced handshake post logic post swap, including reset of SOC, SOH counters. And talking about the telematics fault handling, prioritize battery faults to backend during after swap for traceability. All right. Now talking about the user interface and user experience feedback, in-vehicle HMI, in-vehicle human machine interface should notify user only about invalid or unsafe swap batteries to prevent any kind of any confusion. Now talking of sample swap diagnostic flow, the first is battery ejection event. Okay. And within this battery ejection event, first you have to shut the contactors. Next you log pre-swap BMS data. Next you transmit healthy summary to backend and then you mark battery released. Okay, this is how you eject the battery. Next, when it comes to battery insertion event, first you boot the BMS, handshake with VCU, run the pre-charge, insulation resistance and contactor check. All right, talking about transmit DTCs, if any, and SOH, SOC, bind to vehicle via vehicle identification number or tag. And coming to the drive event, once the regular DTC reporting continues or abnormal behavior, example overrun, thermal overrun, and this kind of abnormal overrun, it triggers the swap required flag. All right, then you return to the swap station, and once you reach the swap station, you with the help of backend compares the battery diagnostics over time, and batteries with repeated or critical faults are quarantined or recycled. Okay, now talk further typical fault scenarios in swapping content. First is what is the major fault? Mounting error. So mechanical lock sensor failure, the manual inspection or swap retry. Coming to CAN bus timeout, the battery CAN node unresponsive and check connectors retry BMS boot. Talking about the temperature deviation, the pack overheated during the last trip, prevent reissue until cooled. Now talking about the SOC spoofing, the battery falsely reporting full charge, cross check with history usage. Okay, so in this table you are clearly seeing the fault, the cause and the remedial action. So in summary, what are the various areas? The battery ID, use secure binding, diagnostics, extended the DTC catalog for swapping use cases, the cloud backend, maintain full history for battery ID, and coming to telematics, synchronize SOC, SOH and trigger alerts, and talking about firmware, ensure auto compatibility across the stations. All right. So I hope all of you got the role or the importance of diagnostics when it comes to swapping, the battery swapping, and its application in the swapping stations.